Good morning, everyone. So we're going to pick back up here in Chapter 5, just a couple more slides on Chapter 5, and we'll be into Chapter 6. I actually have two slides that we're going to use here in Chapter 5 that are the first two slides in the Chapter 6 slide. So the very next slide will be actually from that Chapter 6 set of notes. So when we get there, you might want to have the next set of notes available, or just know that's where the slide's coming from. So what standard enthalpies of formation are referring to are the enthalpies associated with forming a compound from its elements in whatever the most stable or standard state those elements happen to be at room temperature. So carbon's most stable or most standard state at room temperature is carbon graphite in solid form, oxygen's O2, hydrogen's H2. So like forming CO2, we would form it from its elements in carbon graphite plus O2. And the enthalpy of that reaction, you might say, well, what's the delta H of the reaction equal to? Well, the delta H of a reaction usually doesn't have the per mole in it. So the delta H would be minus 393.5 kJs. So if we form 1 mole of compound, then the delta H of that reaction is telling us the heat of that reaction is per mole of that compound that we're making. It's like standard enthalpy of formation. So it's the formation enthalpy for that product in units kJs per mole. And then the utility is that we can start using these delta H's here, these delta HFs, to take the sum of the products minus the sum of the reactants, so that you can think of your delta H as the final minus the initial. So it's just the sum of the final of your products minus the sum of the initial, the reactants. We just have to take into account the coefficients in the reaction, of course. So if we look at a reaction like the one below, where we have CH4 plus 2O2 goes to CO2 plus 2 water, one is we want to make sure to pay attention to the physical state, that the delta HF of the gaseous water is different than liquid water, as we would expect, so physical states matter. In fact, if we wanted to calculate water gas to water liquid, we would just take the delta HF of the liquid minus the delta HF of the gas. So we would have the delta H of that reaction. Now, for this particular reaction, for the CH4 plus 2O2 goes to CO2 plus water, 2 waters, what we would do is just take 2 times the delta HF of H2O gas. So that's 2 times minus 241.82. So this is if we're trying to find the delta H of the reaction. And I might be specific here, that's 2 moles for water times 241.82 kJs per mole. So the mole unit cancels. And then we're summing up the products. So I'm going to take 1 mole times CO2's delta HF, which is minus 393.5. So the mole cancels there too. And then we're going to subtract the reactants. So we're subtracting the sum of the reactants because we're going final minus initial. And so that here we have 1 mole of CH4. And CH4's delta HF is minus 74.8. So again, the moles canceling. Now, we don't see O2, but again, O2 is the one that's defined to be 0 here. O2, we just have to recognize that the delta HF of the element is equal to 0. So anything in its elemental form, most stable form at room temperature, would have a delta HF defined to be 0. That's just because if you imagined writing the formation reaction of O2, it just comes straight from O2. So the delta H has to be 0 there. And so then if we do this arithmetic here, now the only tricky thing is just keeping the minus signs straight, but I just do 2 times negative 241.82 on my calculator. Then I do plus the 1 times negative 393.5. So I'm just being very specific of using the minus signs where they are. I try not to really think too much about this. I just do 2 times the negative plus the negative 393.5, and then minus the negative 74.8 leads me to minus 802. That's minus 802.3. And it's not per mole because we've got rid of the mole unit, so it's just kJs. So delta HFs are convenient. If we had delta HFs for all the reactants and products in a reaction, we can very easily calculate the delta H of the reaction. Now, these are ultimately coming usually from experiments like the calorimetry experiments we were talking about in section 5.5. So a lot of these numbers themselves come straight from experiments that were like bomb calorimetry type experiments to determine those numbers that we could put into tables and then use accordingly. Now, you see these reactions. I just wanted to make sure that we're seeing like how and why the delta HFs work the way they work. You might be a little confused on how it is you can have a reaction to form a compound, and we're just using that one reaction, that delta HF here. How does this work? Well, it really comes from Hess's law. And so if we think of Hess's law for forming CO2 from its elements, so we can imagine maybe the process of Hess's law is, well, let's write out that reaction, and let's understand that the delta H of the reaction would be minus 393.5 kJs per mole times 1 mole, because there's 1 mole of CO2 in the reaction. If we then form 2 moles of water from H2 and O2, and I've just essentially doubled the coefficients from the formation reaction to form 2 moles of water, and so I've taken the delta HF minus 241.82 kJs per mole and doubled that quantity. And then the CH4 reaction, we can write this reaction, imagine adding it up, but I have to flip it to put CH4 onto the reactant side. So when we flip a reaction, we flip the sign of the delta H of the reaction from like Hess's law. So if we rearrange the reaction, we flip it, we have to subtract that or take the negative of that delta H of reaction. So it would be negative 74.8 kJs per mole times negative 1, since we flipped the reaction. And so then, just like Hess's law, if we add up these reactions, the graphite is on both sides, cancels out. The H2 is on both sides, cancels out. And that's it. So we end up with CH4 plus 2O2 goes to CO2 plus 2 water. So it's really just a consequence of Hess's law that the delta HFs work the way they work and allow us to use them to calculate the delta H's of reaction. It's very easy, just summing up the products minus the sum of the reactants. Now, there's one last topic in the chapter, that's bond enthalpies. We also talk about these a little bit more in chapter 8 once we learn how to sketch Lewis structures. Right now, it's a little tricky sometimes for us to give you a molecule because you may not know the type of bonds it has. I mean, I think we know oxygen's double bonded, but again, if you forgot that, I wouldn't be surprised, because we don't really go over how you know that there's a double bond between the two O's until we get to chapter 8, as opposed to, say, a triple bond or a single bond. So here in chapter 5, if we're going to give you a question that relates to bond types, we have to kind of show you the structures. Like here we have CH4, where we see that we have 4 CH bonds in this molecule. We have 2 O2 molecules with double bonds between them. And then we form CO2. CO2 is double bonded, so we have 2 carbon-oxygen double bonds. And then water forms with single bonds between oxygen and hydrogen. And you can see here that depending on the type of bond, it has a different bond strength. The energy it takes to break a CH bond is 413 kJs per mole. What this is corresponding to is going to C plus H. If we want to break the CC bond, this would be going to 2 carbon atoms. So to separate the atoms in the bond, to break the bond, always takes energy. We have to put energy in. That's endothermic. So breaking bonds is always endothermic. But if you imagine making a bond, if you could take an oxygen and a hydrogen and pair them together to make the OH bond, then that's the OH bond strength is 463. So this would be minus 463. So minus 463, because we flipped that reaction. So now making bonds is exothermic. So if breaking bonds is endothermic and making bonds is exothermic, then a given reaction like the one here, whether it's exothermic overall or endothermic overall, has to do with, are we forming weaker bonds or are we forming stronger bonds? And so we can get a sense of that. I'm actually have the numbers worked out on the next slide, but we can get a sense of how much energy does it take to break these bonds? Well, that would be 413 kJs per mole. And there's 4 moles of that bond that we have to break. because there's 4 CH bonds. And then we have to break 2 of the O2 bonds, and that's 495. So 495 kJs per mole times 2. Now, this here's a model. This is one of the trickier concepts to get maybe in this chapter, that this model here is like estimating bond strengths where every molecule CH bond isn't exactly the same. Like you could have a CH bond in something like ethylene or acetylene or ethane or methane, and all those CH bonds are a little bit different in their bond strengths, but we're kind of averaging them out. So when we use this technique, it ends up being kind of like an averaging where we get an approximation of delta H. Everything else in this chapter is a direct calculation. There's nothing that's really approximated per se in any of the work we've done outside of this topic here. So we're going to approximate delta H's here because these are like approximate or average bond strengths for those types of bonds. And so now if we want to break these bonds here, that's going to take some amount of energy. So if we break all those bonds, 413 times 4 plus 495 times 2, that's 2642. kJs of heat have to be absorbed for those bonds to break. Now, again, this is a model. It's not exactly how the reaction proceeds. When we burn natural gas, it doesn't just spontaneously break all those bonds and then have them reform in that fashion. But this is a way that we can try to understand the relative energy this reaction is coming from, the difference between breaking all those bonds versus the energy we would get back when we make the new bonds. So what if I take the collection that we would have now of a carbon plus 4 hydrogens and 4 oxygen atoms that have been freed up from the bonds that they were in these molecules, and then pair them together in such a way that I get the CO2 and the 2 waters, where I'm making all of these bonds here in the products. So I'd be making 2 CO double bonds, and the CO double bond is 699, or 799 actually. CO double bond, 799 kJs per mole. And there's 2 of those bonds that are being made. And then the OH was 463. Times 4 moles. And so let's do that math, 799 times 2 plus 463 times 4. That's 3450. But notice how we have this reaction flipped. We're forming these bonds, not breaking these bonds. So so it would take 3450 to break all those bonds, or we're going to get back minus 3450 when we form those bonds. So it takes 2642 to break all the bonds, and we're getting 3450 back when we make the new bonds. And so now our approximate delta H is going to be approximately equal to 2642 minus 3450. I think that's 808. I hope it's 808 because that's what it should be. Yep, minus 808. And so, one, this is an approximation. The real value should have been 802. So the value we were getting on the previous slide from the delta HF approach, that's the real true delta H of that reaction, not an approximation. Here, this approximate method got pretty close. It was only 6 kJs per mole off. So not a bad technique for approximating delta H's of reaction. But the value or the utility of this approach is that we're seeing the reason why the reaction is so exothermic is we're just making a collection of bonds that are stronger. We're making a collection of bonds that are harder to break than those that we started with. And this goes back to that potential energy picture, that when we create fuels, they're sort of like at the top of the hill, of that potential energy hill, then they break their bonds and they go down the hill, form something more stable. And that difference of energy that's given off comes off as kinetic energy that you can use to move a car, heat up an object, etc. And so it's like showing us why a reaction that's exothermic is exothermic, because we're making stronger bonds. If you imagine a reaction that takes place that's endothermic, you would imagine it's endothermic because we're making weaker bonds. So that would be The endothermic reaction would just be the opposite of this type of reaction here. So this slide here is just kind of showing the math if we wanted to write this out and make sure that we're picturing this. Again, this is in the chapter 6, second slide of those notes, of just the CH4 plus O2 breaking all those bonds. Takes energy to break those bonds, and then we're getting energy back when we make our new collection of bonds. And whether a reaction is exothermic or endothermic is just the balance of how much heat did it take to break the bonds and how much heat do we get back when we make the new bonds. Okay, and so another consequence or something else with this technique is seeing that it's actually reactants minus products. If you think of the way this technique is working, this using bond enthalpies, we're summing up the energy it takes to break the bonds in the reactants, and then we're subtracting the energy we get back in the product. So our delta H here is being approximated by taking the sum of the broken bonds in the reactants. And the symbol for bond strength is usually D. So it's the bond strength of the broken bonds in the reactants minus the sum of the formed bonds in the products. And so these signs here are just the summation. So the summation of the bonds we have to break, but in the reactants, and then minus the products. This is the only equation I can think in this chapter where the delta goes reactants minus products, but it's just a consequence also of Hess's law. Just seeing here that Hess's law is just being followed by what's the delta H for the forward reaction here to sort of atomize the reactants, and then we're forming our new bonds by taking all those atoms and putting them back together in a new form. So it's really just a consequence of if you can add reactions up, you add up their delta H's. So the reason why this becomes reactants minus products is just Hess's law. It's just following the right way to apply these equations so that they add up to the desired reaction. Okay, so there's a few problems that you'll see either in the homework or on the daily quizzes or on practice exams where this topic, just remember, reactants minus products. Okay, so then if we come back to like our very first reaction we looked at in class was that H2O2 reaction. And it becomes really a prototype because it shows us a combustion reaction, shows us a reaction taking place with a kaboom. We can see energy being given off. It allows us to talk about potential energy versus kinetic energy and seeing the potential energy loss coming off as kinetic energy like we were talking about in chapter 1. And so when a spark is given to a mixture of hydrogen and oxygen gas, and we have this violent reaction taking place, which statement do we think is true? So does the reaction give off energy because its products bonds are more stable? That's another way of saying stronger than the reactants bonds. Does the reaction give off energy because its reactants bonds are more stable than its products bonds? Or does the reaction absorb energy? Is the reaction absorbing energy because of something to do with the reactants versus products bonds? So first off, is energy being given off in this reaction? Or is it being absorbed? Violent reaction, combustion reaction, energy is being given off. So energy is coming off this reaction, and then it's because what we were saying before, the products bonds are more stable, they're stronger. That's why this reaction has that energy associated with it. Okay, so it's really the reason why exothermic reactions are exothermic has to do with bond strengths being stronger in the products, and then endothermic reactions being weaker, forming weaker bonds in the products. Okay, so that kind of takes us through chapter 5. I mean, it would probably be good to do a review. I was thinking that we could probably do some review today. We kind of need to move into chapter 6, though. I think the second half of chapter 5, the problems are, there's two forms of calorimetry, the coffee cup and the bomb calorimetry, and then we have Hess's law, and we have heats of formation, and then what we just talked about, bond strengths. I think those problems almost all look the same. There's not a lot of variability in those types of problems that you're going to see. You know how a stoichiometry problem, there's like 50 ways we can ask a stoichiometry problem. There's like 2 ways to ask each of those topics questions. Like on calorimetry, we can either ask you to find the delta H given the temperature change, or we can give you the delta H and ask you to find the temperature change. It's like one or the other. And the same thing with like Hess's law. We can give you a bunch of reactions and ask you to find some unknown reaction. That's about the only variation of that question. So there's only like one type of Hess's law question that you can expect. We'll give you 2, 3, 4 reactions and have you sum them up in the proper way to get the delta H of some unknown reaction. Enthalpies of formation, there's like 2 ways to ask that question. We either give you all the reactants and products delta H's, and usually not the one thing that's an element. That's kind of the one caveat there, is you have to know what the elemental forms are. There's a slide back in chapter 5 if you forget and want to review that. But then the other thing we can do is ask you to calculate delta H like we did today, or maybe we give you delta H and we give you all but one of the delta HFs and you have to solve for the delta HF. You see, so most of the questions in chapter 5 have like 1 or 2 ways of asking them. And it's usually the early part of chapter 5 that we might need to review. So we'll look at some of those review problems when we get closer to midterm 2. Just to get us set on our calendar, we have today and tomorrow, next Monday and Wednesday for lecture. Then we have fall break, Thursday and Friday next week. And then we're taking our midterm Monday night again. So we'll have Monday before that for review. Hopefully a little bit of time on Wednesday for review next week as well. Okay. And then also, when we start chapter 6, we kind of do start a new unit almost of building towards molecular structure is kind of the goal in chapter 9. To get to molecular structure and shapes of molecules and properties of molecules like polarity, we have to get at understanding bonding. Bonding is in chapter 8. To get at bonding, I think we have to understand why nuclei are different and behave differently. That's chapter 7, is understanding different nuclear trends, why sodium behaves like it does versus magnesium versus the non-metallic elements. Why do they have their periodic trends? It's chapter 7. And then to understand that has a lot to do with the electron. The properties of the electron have a lot to do as we go from left to right across a periodic table on why elements vary in their properties. So that leads us into chapter 6 to kind of first talk about the electron. So we kind of go electron properties, chapter 6, nuclear, like the proton properties into chapter 7, and then bonding into molecular shapes in chapters 8 and 9. So for chapter 6, just to give you a quick summary of the chapter, we're going to talk about light to start the chapter. So we're going to talk about the wave nature of light. And that really has to do a lot with the wave nature later we'll see for the electron. So light is a wave that also has particle-like behavior, or can be described like a particle at times. It has the wave-particle duality, if you've heard or seen this in physics class. So we'll talk about some of that duality and some of those topics. And then the electron also has those same kind of dual properties, where it's more discretely a particle, where a photon or a light wave is not a particle, but the electron is a particle that also then has a wave-like behavior associated with it. So there's a lot of relationships between photons and electrons. And then also photons of light can cause electrons to be ejected from metals, or it can cause bonds to break. So we'll talk about some of those processes too. We'll talk about the quantized nature of energy, and then line spectra, something called the Bohr model, which gets at the energy levels of a hydrogen atom, which you can see from an emission spectrum that we'll talk about. Then we'll get into the wave behavior of matter, the wave behavior of electrons, and then basic quantum mechanics, nothing too tricky. If you get deep into physics, go into physical chemistry or physics, you'll hear more about quantum mechanics. We'll just get into the very, very basics of it and show you some shapes of basic atomic orbitals, so we can try to understand representations of orbitals and the electron configurations. I think electron configurations are the one thing that students usually remember from high school. So if I said like the electron configuration, like carbon, do you guys remember doing like the 1s2, the 2s2, 2p2? So the end of the chapter does build towards something you've probably seen before in determining electron configurations. And so we'll get there towards the end of the chapter. And so let's start with the wave nature of light. And so we have here to say sort of 2 different light waves. The difference between the 2 light waves is their wavelengths are different. So here we have a longer wavelength. A wavelength is symbolized with the Greek letter lambda. So here we have a longer lambda. This lambda here is a shorter wavelength. And so if you start thinking about how perhaps this is the same distance, imagine this is 0, this is 1 meter, this is 0, this is 1 meter, that the time it takes both of those light waves to reach that 1 meter target is exactly the same, because light particles travel at the speed of light, regardless of their wavelength, regardless of their frequency. And so if both of these particles are going from the 0 to 1 meter in exactly the same amount of time, then we're going to have more cycles completed for the shorter wavelength. So if we start thinking about the frequency usually takes the symbol nu. So nu is the frequency. And the frequency is the number of cycles completed, number of like wavelength cycles per unit time, say per second. And so for the wavelength in A, it's like we get one wave cycle and then we get a second wave cycle. So this frequency here would be 2 cycles per unit time, which we don't know what the unit time is. Let's leave that kind of, let's just call this, the frequency is related to 2 cycles being completed per unit of whatever that time is. And whatever that time is the same time in part B. So the wave in part B would be 1 cycle, 2 cycles, 3 cycles, 4 cycles. So 4 cycles being completed per the same unit time, so it's traveling at double the frequency. And so we're seeing a connection between cycles per second, or cycles per unit time, and the frequency. And the relationship becomes related to the speed of light. So the speed of light c is equal to the frequency times the wavelength lambda times the frequency nu. And so the wavelength has units of length, let's say the meter. So some, for example, in A, if 2 cycles is a meter, then 1 cycle would be half a meter. So 1 wavelength, the distance between the peaks here, or the distance of 1 completed wave cycle, would be half a meter. And then if we look in part B, the wave cycle is 0.25 meters, just half of that, because we're completing 4 cycles in a meter, so each cycle is a quarter of a meter. And so this is just really to show you that the wavelength itself just has some unit of length associated with it. So the wavelength would be, say, in meters and SI units. And then the cycles per second, usually the cycles is understood, and so we just call this inverse seconds as our frequency. And then to set the stage 2 frequency, often uses the symbol hertz, which is a weird unit because this is just cycles per second, or inverse seconds. So we use the symbol hertz a lot to relate to the number of cycles completing per second, or for the frequency in inverse seconds. Okay, now, again, it's just important that we know that all light, regardless of wavelength and frequency, is traveling at the same speed of light. Now, I'm sure you've seen this before. This is the electromagnetic spectrum from the low frequency to the high frequency, or from the long wavelength to the low wavelength. Let's talk wavelength first. So the long wavelength is radio frequency. So the radio frequency waves are those long wavelength frequencies. And then our opposite side of the spectrum is the gamma ray. The gamma ray would be the ray with the shortest wavelength. And so this photon of light here would be characterized as having a wavelength that's, a lot of cycles being completed per unit time, a very short wavelength. And so, if we're picturing c is equal to lambda times nu, if we have a very long wavelength, we have to have a very low frequency. So the longer the wavelength, the fewer the frequencies completing per second. And so this is a relatively low frequency. And then if we think of the relatively the relatively short wavelength, gamma ray, therefore has to have a very high frequency, such that they multiply to still give you the speed of light. And so a really high frequency. So this means your gamma ray is completing a lot of cycles. So which wavelength would you be afraid of? This one or this one? And it's, so the short wavelength or the higher energy. So this is our higher energy side of the magnetic spectrum. This is the lower energy side. Now that's useful to know, or probably pretty obvious that we're going to not be shooting gamma rays on our cell phones around at each other. That would probably be quite hazardous. And so the lower energy, longer wavelength, shorter frequency lights on that radio frequency side, and then our gamma ray is that low wavelength, high frequency, high energy side of the electromagnetic spectrum. And then everything else is in between. The in-between would be like X-rays, a little bit lower in energy than gamma rays, then UV rays, then our visible, then infrared, microwaves, and radio frequency. Now, the infrared is just the lower energy past the visible, and then microwaves kind of in between them and the radio frequency waves. Now, sometimes I've wondered, and isn't it kind of weird when you first look at this, like why the visible, why is it where it is, and why is it so narrow? And if you think about it, this has to be evolution, right? When you start thinking about ultraviolet rays, they're the rays that start to carry enough energy to break bonds in your body and your skin and your DNA. They're the ones that are hazardous to us. The visible rays, not so much in terms of being hazardous. Maybe long exposure is bad, so you don't want to necessarily shine super bright, 500 nanometer light around each other. But it's not particularly hazardous to be around visible light like in the room. And so I think it's really good for our eyes to be able to see just beyond what's harmful, right? So that we can sort of be able to sense when we see that really bright light like the sun that we look away. And we've just learned this through obviously being too long into the exposure under those elements would lead to negative outcomes. And so, so I think our eyes are designed to see just beyond the point of what's hazardous. And it's also like if you think about just like sensing temperature, like if you've ever wondered like why does ice water have to feel cold? It's like, well, it better because you're going to freeze if you didn't sense it as being cold. So I mean, we're designed as a species, I think, to be able to sense hazards. And so if we might freeze, it'd probably be good for that to feel cold as opposed to that not feeling cold. And if we're going to look at a light that's hazardous, it'd be really wise or evolution over time has led us to sensing and being able to see that light, and being able to see that light means visible region has to be where it is. Okay, and so the visible region itself is the narrow region from 400 to 750 nanometers. And so if we go to the lower side, this is high energy, this is the UV side. So ultraviolet rays. And so then this would be our IR, lower energy side. So if we go beyond 750, that's going into the infrared side of the electromagnetic spectrum. Let's just do a couple problems of conversion. So what is the frequency of light in hertz? And again, that's just simply inverse seconds. If the wavelength is 725 nanometers, now we should tell you the speed of light or like, this is actually would be a given on test too if you forget this. And I think everybody knows. What's the speed of light? Somebody knows. Yeah, so and the unit matters too. So like 3 times 10 to the 8 meters per second is the one unit that students often know is the meters per second. Sometimes people know centimeters per second. But we often will use 2.998 to be a little bit more precise, times 10 to the 8 meters per second. And even then, like you could, I think it's known to 8 or 9 decimal places of precision. If we needed to know more, we could look this up more precisely. But this is usually the one that I'll use in most of my examples in class so that we have enough decimal places. So I'll often use 2.998 times 10 to the 8. 3.00 times 10 to the 8 is fine too. I think that'll get you through all of your exam questions just fine. But so if we're wanting to solve for a frequency, C is equal to lambda times nu, and then we're trying to solve here for that frequency, so C divided by lambda. This is another problem where it's going to be good to use units, because if we just did C divided by the 725, the units aren't going to work out right, so we have to account for units when we do problems like this. So we'll take 2.998 times 10 to the 8 meters per second, and then we'll divide by 725 nanometers. And I think you see we want to go to meters, or we want to do one of two things. We either want to convert the speed of light to nanometers per second. Probably not the easiest way to do the problem or to think through the problem. Probably easier just to convert nanometers over to meters. And this also then takes us back into our prefixes, that micro is -6, nano is minus 9, pico is minus 12, and I think beyond that we would tell you femto is what's minus 15. But the minus 6, minus 9, minus 12 would be micro, nano, and pico. And so 1 nanometer is really small, 10 to the minus 9 meters. And just think if we did 10 to the plus 9, I don't think it would make sense. That would make the nanometer very big. Nanometer is very small. And this also then allows us to relatively easily put this into our calculator if we do the conversion this way, because I would just do 2.998 e to the 8, but then 725 e minus 9 works. So when I'm putting this in the calculator, I can just put in 725 e minus 9. And so then I get 4.14 times 10 to the 14. The units would be inverse seconds because our meters canceled. We're only left with 1 over seconds or inverse seconds, and that's the exact same unit of hertz. Now, we could have asked for this in gigahertz, and it isn't necessarily a much better looking number. Like the frequency looks very big, and this is the correct frequency. If you look back in the previous slide, the frequency even for radio frequencies was in the thousands, and then for gamma rays was 10 to the 20 or even higher. And so the frequency itself is going to be a big number. So we could convert this to something like gigahertz, and this might just take us back through that mega is beyond kilos 10 to the 3. So mega is 10 to the 6, and giga is 10 to the 9. So if we wanted to convert this to gigahertz, then how would we do that conversion? Well, 1 gigahertz is really big, so this would be 10 to the 9 hertz. And of course I flipped this. So we want the gigahertz on the numerator. So 1 gigahertz would be 10 to the 9 hertz. So if we do this conversion, it doesn't really make it a better looking number because it's still going to use scientific notation, but 4.14 times 10 to the 5 gigahertz. And I'm just showing this conversion because you might see gigahertz somewhere in this chapter, and it's just relating to 10 to the 9 hertz is 1 gigahertz. Now let's compare 2 photons. Let me give you guys a chance to think through this one here. So compare a 725 nanometer and a 625 nanometer photon. Give this one a minute or two. Feel free if you want to come up with your answer and compare with your neighbors. I don't think this is the best worded question as I sit here and read through it. But I think we can all agree that they both travel at the same speed of light. So statement 2 is clearly not true. So they both travel at the exact same speed of light. And then compared to the 725, the 625 has a lower wavelength, which should lead it to have a greater frequency. And so it should have a greater frequency. I think worded this way. It's kind of worded hard to understand. Am I talking about the 625 nanometer photon, or am I talking about the 725? But I think statement 1 is true here. And again, sometimes these questions are, like the test questions, are sometimes hard to interpret. Okay, so let's get into the topic of like how energy levels in molecules are not quantized and how this actually led to the discovery of something about light in the process. And so if we think about striking a metal, so if you shine light onto a metal, it's possible that the light would just be deflected off the metal and nothing happens. And so then you can imagine taking more and more photons, it's like a brighter light source, and you keep shining light onto this metal and still nothing happens. And then maybe you're using like a 750 nanometer photon, kind of like that visible photon that's closer to the closer to the infrared region. And then maybe you say, well, what if we start going towards the UV and we use a higher energy photon? Well, let's also take a step back and say we don't even know that there's energy yet. So like we haven't even yet established that different wavelengths of light have different energy. So maybe we haven't even come to this realization as scientists yet. So we're like, using the red light does nothing with the metal. We use the blue light and it does something. It causes electrons to be ejected from the metal. And so we can cause electrons to be ejected from the metal, it turns out, if we add enough energy. If those photons carry enough energy to cause that electron to be ejected from the metal. You could think electrons in the metal, that there's some energy that those metal atoms are holding onto those electrons with. If we add enough energy, then we can cause those electrons to be ejected. And so this experiment here led to the idea that photons carry energy, and that photons are kind of behaving like a particle. It's like they're almost like a baseball or something, as long as it's a fast enough fastball, which isn't a great analogy, right, because the photons all travel at the same speed. But if the photon has enough energy associated with it, then it can cause the electron to be ejected from the surface of the metal. So it's really not about how many light particles we're throwing at the metal, it's about what type of energy those particles are carrying. And this led to the discovery of photon energy being related to its frequency and wavelength, that the energy of a photon was equal to Planck's constant, which we'll talk about in a minute, times the frequency. And then if you recall, frequency is equal to the speed of light divided by wavelength, the same equation from the previous slide. So C is equal to lambda nu rearranged. And we can also write that this would be equal to hc divided by lambda. And so if you know the frequency of light, then you can relate that to the energy. And so as you go to a higher frequency, we go to a higher photon energy. And then that would be the same as going to a lower wavelength, going to also a greater energy. So if we go to a lower wavelength, hc divided by lambda leads to a greater photon energy. And so this is why like a 400 nanometer photon has more energy than that 750 nanometer photon. So as we go from close to the infrared, close to the UV, we're increasing in the photon energy. The photon's carrying more energy. This is also the photoelectric effect. This is Einstein's discovery that actually led to his Nobel Prize. It actually wasn't the relativity work that he had done. It was the work in the photoelectric effect, trying to understand the original experiment that was actually done by Hertz, who did the experiment to shine different types of lights onto different types of metals, was discovering what's called a work function. For different metals have different work functions, different energy required to eject their electrons. And then later Einstein came in and did the sort of work to understand what was going on, and that was the photon energy discovery. Hertz probably would have discovered it himself, but I think he passed away like in his mid-30s. So Einstein came in, and that's like one of the running jokes, like Einstein just like steals other scientists' work. I don't think that's the case here. I think he was providing the understanding for an experiment that was done that really didn't have a clear explanation, and this ended up being the explanation, the photon energy. And another observation to kind of go backwards on the slide, I guess, is if you think of black body radiation as like the light being emitted from objects that are heated up. So if you think about like an electric stove, how it radiates like a reddish, almost whitish color as it heats up, or even thinking about the color of a flame. I think we all know, like if you have a Bunsen burner with an orange flame, not as hot as a Bunsen burner with that bright blue flame or even close to white. And that's kind of like your eyes seeing the visible photons closer to the if we think of the color, I don't want to flip back on the slide, but the color associated with the 750 nanometer color is like red, orangish. That's the lower energy side of the visible region. You go blue, violet, and then that bright white color, that's getting into the ultraviolet rays on the ultraviolet side, the higher energy side. So glowing objects, the color of the glowing object can tell you something about the heat or the relative amount of energy coming off of that object. And the color itself became associated with the energy, just like the photon energy. So just like this photon here is closer to violet in color, that's our higher energy 400 nanometer photon. 750 is closer to red-orange. So like the color of a flame can help indicate hot flame versus cool flame. Now that lets us solve questions like this that just relate to like energy of light now as a function of its wavelength. So a laser is emitting light with a wavelength of 250 nanometers. What is the energy that this light's carrying, but in units of kJs per mole? So how we would use our previous equation would be E is equal to h nu, or hc divided by lambda. So we could calculate our photon energy. I haven't mentioned h yet in terms of what numerically it is. H is Planck's constant. It's technically pronounced Planck's constant, but I don't like calling it that. I think, can we just pronounce things the American way? And if we go to Germany, we can pronounce it the German way. There's another word in this chapter that's actually a French scientist, and some people pronounce it the French way, and I'm like, I'm just going to pronounce it the American way. So we'll talk about that one later. But Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. And that's a 34. So a really small number. So E is equal to h nu, or hc divided by lambda. And so if we, and this is the energy of a single photon. So just one photon, you can imagine having more than one photon. We'll get to more in a minute, but we'll take 6.626 times 10 to the minus 34 joules times seconds. We'll multiply that by the speed of light, 2.998 times 10 to the 8 meters per second. On tests, we give you Avogadro's number, we'll give you Planck's constant, we'll give you the speed of light, we'll give you most of your numbers that you don't have to memorize per se, but as we do examples, I think you're going to come to memorizing these values. So hopefully you find that most of the numbers we give you on a test, you probably memorize by doing enough problems, I would hope. But then if we're dividing by 295 nanometers, again, we can see, as long as we're thinking about our units, that we're going to want to convert that to meters. So again, a nanometer, 10 to the minus 9 meter. So 6.626 E minus 34 times 2.998 E to the 8 divided by 295 E to the minus 9. And so I get the energy of a single photon of this light would be 6.73 times 10 to the minus 19 joules. And so now what do we think about kJs per mole? Well, this is just the energy per photon. A lot of times we wouldn't write it. Like if I said, what's the energy of the photon, it would just be 6.73 times 10 to the minus 19 joules. But then what we can do is we can convert this to, Avogadro's number. That we can imagine having 6.022 times 10 to the 23 photons of this light, and that would just be 1 mole of those photons. And then we can convert joules to kJs. So 1,000 joules per kilojoule. So times 6.022 E23. Divide by 1,000. So I get 406 kilojoules per mole. So answer B. Now, if we start thinking about that this is, 400 nanometers is roughly the edge of the visible. This is into the UV, so this is a UV range photon. Think for a minute about bond strengths from chapter 5. That like bond strengths were like single bonds were about 400 kJs per mole. This is starting to carry enough energy to break bonds that could possibly be in our skin. So this is getting into the range of being able to break bonds. One of the very last slides, I'm not going to flip there yet, but one of the very last slides in chapter 6 has some connections to DNA and some connections to different wavelengths of light that sunlight carries. And so UV light gets into that range of being capable of breaking bonds because you can see per photon it carries enough energy to break one of those bonds. And so that's kind of like the photoelectric effect, is that the idea here is that metals can release electrons when they're shown or shine light onto them that have this minimum frequency or minimum energy. So as long as you have light that has enough frequency or enough energy to cause the electron to be ejected, then electrons can be ejected. But it becomes like one metal atom and one photon of light becoming at the sort of atomic level. So you can sort of think one photon plus one metal, as long as it carries enough energy, goes to the metal plus the electron being freed, as long as it carries enough energy. And so metals have characteristic ionization energy, so different metals are going to have different energies or different frequencies of light or different colors of light associated with causing electrons to be ejected. And so then this is what led to the discovery of the equation E is equal to h nu. So I think the slide was out of place. This should have been wedged in before we were doing the problem. But so this is just showing us the discovery of Planck's constant, a discovery of E is equal to h nu, and then the ability to solve problems like the previous one. Okay, let's end class with this problem here. So what wavelengths of light are capable of breaking the bond in O2? And so the O2 bond enthalpy from what we saw in the last chapter is 495 kJs per mole. And so we start thinking the photoelectric effect is one photon plus one O2 goes to two O atoms. Just thinking just one single O atom or one O2 molecule. And so we're thinking one photon energy, the energy for one photon versus one O2 bond. What I'm really going to think about here is trying to calculate the energy it takes to break the bond in just one O2, as opposed to 495 kJs per mole. So the number of joules to break the bond in just one O2, we'd start 495 kJs per mole. Then we'd go and convert that quantity, 1 mole would be 6.022 times 10 to the 23 O2 molecules. And then a kJ is 1,000 joules. And I'm only going to joules because I'm going to use Planck's constant later. So it kind of helps me to just go ahead and throw this into joules. So the energy it takes to break the bond in one O2 would be 495 divided by Avogadro's number, and then times 1,000. And so it's 8.22 times 10 to the minus 19. So then what we want to find out is what wavelength of light carries that energy. So what wavelength of light carries that energy? So this leads us into the energy of the photon has to be greater or equal to this energy here, so the hc divided by lambda has to be greater than or equal to 8.22 times 10 to the minus 19. And so what we want to do here is just solve for that wavelength and then address the question. We're so close to being out of time. This is probably a good problem to come back to the start of class on Friday to start with anyways. So why don't we kind of pick up from where we're leaving off in this problem and try to work this out. But if I think it ends up being less than 401 if you happen to work it out in the meantime, I think is what the answer is going to be. All right, so we'll pick up from this one on Friday. You guys have a great day.